Hey everyone, it's Blake, and welcome back to VR Development for Programmers. So this is week 11, optimization. This is the final week of the class. This does cover a bunch of topics regarding just making your game perform better. Some of these things I recommend you do at all times, but certainly if you start noticing any kind of poor performance in your application. Now, if you're on a big beefy desktop like we use for development, you probably have a lot of room to be able to do things and not necessarily tighten down every little bit of optimization. But if you're working on a HoloLens, Samsung Gear VR, Google Daydream, Google Cardboard, any kind of mobile VR, you're going to absolutely need to pay attention to your optimization and know how to do it. The reason why we saved this for last is because premature optimization is the root of all evil, which is a quote by Donald Knuth, who was a famed computer science author. And he's absolutely right. If you optimize things before you're done, you're going to spend a huge amount of time optimizing features that might get cut later. You might spend a lot of time optimizing things that turns out don't actually have a huge performance impact. So the premature part is really important. You need to go in, you need to measure your system, you need to know how it performs. And to do that, we use profiling. Lots of profiling and testing on the device you think you're going to be running the application on. But if you go up to Window and you go to Profiler, this is your profiler. It has two main parts. This is your graphs up here, and then there will be a text display down there. So I'm just going to go ahead and hit play. There's nothing in this particular scene. So our performance is going to be great. We have VSync turned off. We're getting over 1,000 frames a second. Every now and then we spike and we have our performance hit and we go down to a mere 250 frames a second. And again, our target numbers are usually 60 to 90 frames a second. Our overview here will tell us what's taking up a lot of the CPU cycles. So our camera rendering is taking up the most at 60%, and then overhead, so this is Unity Engine's overhead, and then a bunch of other little stuff. And again, we're, in some cases pushing 2,000 frames a second, which is, well, pretty much ridiculous. So, we're doing great. Of course, there's nothing in our scene. One thing I do want to mention, we talked about VSync a bit, and so you'll see that if you go to your Edit, Project Settings, Quality, there is over here on the right, Other, Blend Weights VSync Count, and this is where you want your VSync, and we say don't VSync, because even if we do every V blank, so that's your vertical blank, every time that VSync is an option, if you VSync, all of a sudden you'll see that yes, our game is at 60 frames a second because it has engineered itself to be 60 frames a second, and so it spends a lot of time doing this active waiting for the frame rate to be exactly the frame rate that we want. So we don't want that. We want don't sync. We want to get that data out as fast as we can to the headset, even though it may potentially risk tearing. So yeah, make sure that set it don't sync. All right, so now we have our scene. We have nothing going on in our scene, and we need to get a lot out there. Now, this is a big, beefy machine, much like the machines we have in Immersion Central. So we're going to go ahead and create a new object, and we'll call this spawner, which is a common term used for the creation, the instantiation of a game object. And I am going to put that towards the center. And so on this, I have a script, and all the script does is just goes through a loop and instantiates lots and lots and lots of stuff. So we're going to grab a prefab, and I'm just going to grab the sphere prefab, dump it in there, and I'm going to say 5,000 spheres, which is a lot. It's kind of ridiculous, but it's actually not more than this machine can handle. So I'm going to go from, they can spawn anywhere between -25 to 25, 105, 25. So there's a 50 meter square that's 100 meters tall, and so they will show up anywhere inside that shape. And so now, when I hit the play button, all of a sudden we have 5,000 spheres, and they're all over the place. And we're going to pull up our profiler, and we're going to see what that looks like. Okay, so up at the top we have our graphs. Right, and we can see A lot of this is the orange, which is the physics engine, and then there's a fair amount that's green, which is graphics, so it's a good split between rendering and doing physics calculations. And we can see here the camera render is, bouncing around between 1/3 and half, and then the physics processing is about 1/3, but then there's some other physics stuff that's going on. So it's about half physics, half rendering, and that's what we're seeing up here. And it bounces around a little bit depending on how many objects are on the screen, what they're doing. And if I'm moving windows around, that actually has an impact, as you can see. All right, so we're going to go ahead and stop it. So 5,000 is a good number. It has, that's a nice balance for this machine. Again, you're going to want to test on the machine that you're using. Your HoloLens is not going to be able to do 5,000 spheres by any stretch of the imagination. Now, one of the things you want to keep in mind as you're doing your rendering, if you think you have an object that is suspect, right, and you're saying, I think, maybe my lighting is causing me problems, you can turn off your directional light at runtime and you can see what impact that has on your profiler because it's all live. And sure enough, the amount of processing power drops dramatically when there's no lighting in the scene, and you get a great 60 frames a second, although you can't see anything. So, being able to turn things on and off dynamically is really, really nice for being able to debug. Right? So keep that in mind. So some easy optimizations that you can make. Well, one is removing objects, right? I mean, right now we have 5,000 objects. That's a whole bunch. If we move that to, 2,500, not 25,000, instead of being comfortable in that 30 to 60 frames a second, what we're seeing is we're going to be very, very solidly in the 100 frames a second. So all of a sudden there's been a huge improvement in performance, and there's still more spheres on the screen than we really know what to do with. I mean, it's still a ridiculous number of spheres. And again, these are very, very simple models. So, as your models get more complex, and instead of having, 100 or 200 faces, they start having thousands or tens of thousands of polygons. That's going to have a much larger impact on your performance on a per object. So I know these numbers are really big, and you're like, if you can have 25,000 or 2,500 things, that's more than I'd ever need. Well, yeah, except for these are kind of simple things. So just keep that in mind. Reducing and removing materials is another way. Right now I'm using default material, and this model isn't a multi-material model. Some models, especially the ones you can get online, are much more complex models. Some of them have millions of polygons, and they'll have multiple materials inside that model. What happens when you have a model with multiple materials is under the hood, there's actually multiple renderers that are going on and keeping track of it. And so a lot of cases, if you have a bajillion different materials on something, that's a different bajillion renderers, and it can have an impact on performance. So removing materials isn't something that is super duper common, but it is a way to save some processing. Low poly meshes, so we're going to go ahead and crank this back up to 5,000 objects. Actually, let's go for 7,500. Let's push the realm of good taste. Actually, no, I'm going to bring it back to 5,000 because I know the physics, in this case, as I add more and more spheres, the physics gets more complicated. The rendering the rendering scales linearly with these simple models, but the physics does not. So I'm going to keep it at 5,000. So again, we have the spike when there's the big pile up, and then we have this 30 to 60 frames a second that we seem to be consistently happy at. And that's our standard spawner. We're going to duplicate that spawner, and we're going to just turn off our source one. And so I have a dodecahedron. Right, so dodecahedron has 20 triangles on it. Right, so this is a dodecahedron that is made to look like a sphere, so it's smooth shaded. So you can take a look at it. It looks pretty spherical. You can tell that there's some rough edges and whatnot, but it also has a sphere collider, so it's going to behave like a sphere. So it looks enough like a sphere. It's going to behave enough like a sphere. It's going to pass the duck test. It's going to look like a duck, quack like a duck. And a lot of times people won't care that much. And so again, we're going to do 5,000 of these, and we're going to see how much of a performance impact that's going to have, right? We're going to keep testing, and again, it starts low, and then there's the big collide, and then after this goes and things kind of even out a little bit, we're still in that 30 to 60 frames a second. It's a little hard to tell, and it might be hard to see on the video. We're not hitting that 30 frames a second as hard as we were, so we're probably really averaging closer to 45 frames a second than we were with the sphere colliders, or I'm sorry, with the sphere models. What else? Level of detail. So we've talked about level of detail. Level of detail is real neat. So I have another one ready to go. So this is a sphere using level of detail. Now, when you are close to the sphere, it is going to render as a sphere. When you are far away from the sphere, it is going to render as a cube. Now, the collider under the hood is still the sphere collider, right? So it's always going to behave like a sphere, even though it may look like a cube, which sounds a little weird, but it is, well, because it is. But, you know, so it doesn't change the underlying math behavior, it just changes what it looks like when it renders. Now, and again, in this case, this is kind of a trivial case. If you have a really fancy model of like a ship or something like that, when it's far in the distance, you're not going to be able to make all those details. And then when it's a lot closer, you're going to want to increase the level of detail because it's going to dominate more of your scene. You're going to be able to see those fine details. In this case, this is a oversimplification. This is kind of a contrived case, right? But I'm going to go ahead and hit play on this. And so you'll see that all of these boxes are coming down, and then as they get closer, they turn into spheres. And so the physics is taking up as much processing as it did before, but then the rendering is actually going to take a lot less. Now, in this particular case, it's not going to take hugely less because there's still a lot of spheres, and the number of triangles between a given sphere and a cube isn't that great. You can see that the cubes are rolling like spheres, which looks a little weird, but and again, so our performance here is kind of, you know, between some of the other tests. It's still in the same neighborhood, but again, if you're talking about having models that have hundreds of thousands, if not millions of polygons, then being able to have a level of detail and having the game engine handle that transformation between one model to another really, really makes a lot of sense. And again, this is, you know, there's a lot of difference between a sphere and a cube. So that's, you know, designed to demonstrate without going into all the gory details. Remeshing things at different resolutions is tricky, so that is something that we can talk about in detail if you have a particular need for that. Textured meshes. So, you know, in this case, we've had a lot of solid color objects. Adding textures to things can add a lot of those fine details that removing the geometry would get rid of. So using, you know, just textures, bump maps, roughness maps, some of the material properties, all of those things are going to be less computationally expensive than lots and lots of polygons, especially since all of those polygons get rendered twice, one for each eye. So, you know, keeping that in mind, having those textures is a good way to really improve performance in a lot of cases. Lighting, right? Lighting has a dramatic impact on performance, right? If I turn off this directional light and then poof, all of a sudden my performance gets way better because it's not having to do any shading or anything like that. And that's not terribly surprising. It's also not super helpful in this case. So let's go to some cases where it will help. So I'm going to go ahead and disable this directional light, and I'm just going to duplicate it. So directional lights aren't that expensive. They're somewhat expensive. What is much more expensive than a directional light is if I create a, not a spotlight, a point light. A point light is much more computationally expensive. I'm going to bring it up here, and it's going to have a range of 100 meters so that it can light the scene. I'm going to give it a higher intensity, right, so that you can see it, and So now we're going to run that, and we're going to see that there is a dramatic performance hit as things are getting rendered with this. Now, one point light isn't that bad, right? If we switch it off with the directional light, the directional light is much less computationally costly, and we'll see that again. I'll do that's with both lights, and now this is, so we are solidly at 30 frames a second, a bit under, but now that we've turned on the point light, we're still at 30 frames a second, but the amount of time that we're at higher than 30 frames a second is a bit less. So it's definitely more computationally expensive, and this, of course, becomes more and more pronounced as you get more and more lights in the scene, right? So we're going to go ahead and create an empty game object, and we're going to reverse the orientation here, right? And we're going to duplicate the directional light. Well, it's not really a directional light, it's just called that, which is since I copied it. But it's another point light. Now, the frustrating thing is point lights, people like to use point lights because they are very reminiscent of incandescent lighting in our homes, or, a light bulb kind of light that we are used to. I'm going to drop the intensity here a bit since I got more of them in the scene. But then again, I'm going to hit play, and there's all of these beautiful complex shadows. Right? It's really looks neat. It's beautiful, and our performance is just in the gutter. Right? We're not even getting 15 frames a second. Interestingly, it looks like the physics is dominating it. Lighting and physics. I didn't really expect the physics to have the lighting have an impact on the physics, but this is why we measure it. And it may actually just be that the physics takes what the physics takes, and then the rendering is happening at a lower priority, and then since we have more processing to do than we are doing, we're just losing out on seeing that. So you can see the scene looks neat now. We're still at 15 frames a second, so the performance is absolutely not acceptable. So one directional light is certainly better than all of those point lights. And even if I had 4 directional lights, we can do that too. That'll show a very pronounced impact on performance. So go ahead and do directional light there, and then duplicate the directional light. Now, directional lights don't actually matter where they are, so I'm going to change the angle of the directional light. Oh, it's turned off. Let me turn these back on so we can see what we're doing here. We'll turn on both of those, and then we'll turn off all of these guys. And then so we have these directional lights, of course, with multiple. We're going to reduce the intensity so that we can actually see anything. Right, and then we can also change the direction and the color, just making these directional lights a little more distinct because it's kind of hard to tell. Right, so now we have 2 of them. So we have lighting from 2 different angles. And then we're going to add purple, and it's going to come from a very different direction. So what we should see, if I'm doing this right, is that the different faces, or the different sides of the spheres are going to be colored kind of different colors. But I haven't practiced this part, so we're just going to see what happens here. All right. That looks pretty good. So we're going to hit play. Or see, yeah, so you have different shadows of different colors because of the different lighting, and yeah, some sides are more orangey, other sides are a little more green. And again, we're really chugging along. It hurts performance, but turning that off, turning this on. The directional lights aren't as bad as the point lights. Now, the spotlights are another kind of light, and those are less impactful than either point lights or directional lights because spotlights have a very definite cone of lighting, and by having that definite cone, it means that objects outside of that aren't getting as much light, so it allows for a lot of optimization. Physics, as we're seeing, physics can have a major impact on performance. If something seems complex, it probably is, right? So you can look at simplifying some of your physics. One of the other things is the kind of physics that you're doing. So in this case, we're going to go back to a simpler lighting scenario. We're only going to have 2 lights on. All right. So that's still, we're hitting 15 frames a second, which we weren't getting with only 1 light on. And then we even out a little bit better. We're still at 15 frames a second, so actually having those 2 lights on is a bit much. So I'm going to turn one of them. Oh, that light isn't actually providing a whole lot of light. It must be aimed in a bad way. There we go. So we're going to leave this 1 light on because that's going to give us good performance. And then we're also going to talk about our spawner here has this sphere with a level of detail, and the collisions happening with that are happening on spheres. It has a sphere collider. If we have our dodecahedron, but then we have a mesh collider with it, so here's our dodecahedron with a mesh collider, and as you can see all of the triangles, and so it's actually going to do the physics calculation based on all of those triangles. And that's actually a lot more complex than a sphere. So I'm going to bring up this dodec as a prefab. And so now when we hit play, they will behave like dodecahedrons, which means they will actually eventually stop, or many of them will, before they roll off the table. But you can see that the physics calculations are now absolutely dwarfing the rendering calculations. So where it had been about half and half, the physics are dominating because those meshes are so much more complex until the objects come to a rest. When the objects come to a rest, Unity marks it as stationary object, and then it eliminates the physics calculations, and now we're at 100 frames a second. So physics is good, and using it is good. Just be mindful of how complex your interactions are all at once. And so we had this giant pile of spheres or dodecahedrons. It was really, really complex until things settled down and stopped. With the spheres, they didn't settle down and stop nearly as much. So keep in mind as you're doing, keep testing. Fixed update. That's in your code, so it's much like your update statements. Try to keep your code out of your fixed update. If your fixed update is not performant enough, it's going to slow down your engine, and actually it's going to break the physics portion of your engine, and your objects will start to break the laws of physics. So your fixed update is one that we actually want to try to stay out of as much as possible, unless you have something very physics oriented. Your update statement, that's where all of your code should be. If you're not using your update statement, then you can actually safely delete it. It doesn't have to be there, and it'll actually improve performance, because if there is no update statement, then the engine will skip over calling update on that object. And again, an empty function call is extraordinarily fast, so it's not like it's that big a deal if it's in there. So this is where it is like, don't spend hours going through all of your code to try to get rid of your update statements unless you happen to know that for some reason empty update statements are a performance hit. But it is something you can do. Coroutines we've talked about a bit. We have a whole supplement about coroutines. They do help performance in a couple of ways. One is it branches processing. You don't have to worry about thread management, that kind of thing. It also means that you can distribute a processing load over a number of frames instead of having everything happen all at startup. So right now what happens when I hit play here is all of these are getting created at startup. Another way to implement this would be to have an update routine that over time, as that update routine gets called, slowly reduces spheres, and it would help probably reduce this giant pile of spheres that's happening all at once. And it'll also just kind of even out the instantiation. So sometimes when your application starts, it does a ton of instantiation at the start of a level, and there's this big wait time. You want to try to avoid that if you can, especially when people are in VR. And so using a coroutine to kind of extend to expand the instantiation time from start to over a number of frames is a great way to kind of distribute some of that performance. And then reducing searches. So this is actually a good one to talk about. So in our code, so say we have our code here, and this particular code does not need to find a camera, but again, so this is going to be a little bit of a contrived scenario, but stick with me. So say we need our camera, right? And so we're going to have our void update, and we're going to have our, in our update, and we're going to say var my camera is equal to game object dot find object of type camera. It is not uncommon to have to look for the main player camera. This is something that happens a lot. When you do this, this is going through all of the game objects, looking for anything that has a camera component, and then returning the associated game object. In this case, since it is find object of type, it is going to stop at the first one, but if you did find objects of type, it is going to go through all of the game objects and return a list of cameras. In a lot of cases, we don't need to do this, right? So there's a couple of things that we can do. First of all, we can just move this up to our start, right? And so now we can have a camera variable in, instead of my camera down here, we can just say camera, my camera, right? And so what it's going to do is at startup, it's going to do the search once. It's going to find the game object, return it, and then in our update, we can just use it. We're not constantly looking for that camera every single frame. The only downside is sometimes things don't get initialized the way we think they do. So this is a little risky. So actually, my general preferred technique is if my camera is null, then I do this. Right. So I just do a quick null check, which is very, very, very fast. And then only if the null fails do I perform a search. And then after that, I can, well, so you still need to check if it exists. So in case this search returns nothing, then you have a problem. So you still need to do a check. But in this case, you're doing it only when you absolutely need it. You're only searching when you don't have it. And that's much more performant because, again, this update is happening anywhere, and hopefully in our apps, we're at 60 to 90 frames a second. So 60 to 90 times every second, we're doing this search over and over and over again. If we can cut that down to something as simple as a null check, that's a huge performance benefit to our application, or it can be. So if you have a script that's slow and you're doing find objects, that is a likely candidate. The other thing that we can do is mark objects as static. So I'm going to click on the floor here, and I'm going to mark this floor as static. And again, in this case, we only have 6 sides, which is 12 triangles. So we're not going to see a major performance boost on a cube. But what it does is when you mark this object as static, is it tells the game engine that this object is not going to move. It doesn't have any dynamic behaviors, and so it is just going to hang out right there. And so a lot of these parameters all of a sudden become unused, right? It can optimize a whole bunch of things. It can optimize its lighting. It can optimize all kinds of stuff. This also works for lights, right? If we say our lights instead of real time is baked or mixed, right? This means that the engine can go ahead and optimize that for you. And I have seen cases where, again, in a more complex model, especially like something you can get out of a CAD tool or something like that, if it's your environment and you know it's not going anywhere, marking it as static can have a dramatic improvement in performance, because that means that a lot of calculations happen in edit time and are just cached and ready to go for runtime. One other thing I do want to mention real quickly, because we haven't talked about them much, are blend probes. So I'm going to go ahead and I'm going to turn on our cool funky lights. I'm going to turn off this light. And then I'm going to go back to our spawner. I'm going to find I'm going to go and we're going to have a shiny sphere. So I'm going to duplicate this shiny sphere, and I'm going to change the shiny sphere's material to be, I think, new material 1. Yeah, this is a fairly shiny material. And so now we're going to have our spawner spawn 5,000 shiny spheres. And that's not going to look a whole lot different. Like, they're going to render a little different, and you can tell that these spheres are shiny. And there's lots of lighting. Oh, I didn't mean to have all 4 of these lights on. Hold on, I'm going to just turn off. I'm going to turn off 2 of these guys. There we go. Keep our performance somewhat sane. There we go. All right, so now we're going to have a nice mix. Ooh, window profiler. There we go. All right. Happy medium. We're still under 30 frames a second, so this isn't great frame rate. But we have lots of spheres. They're really shiny, and they're reflecting off of each other, which is really kind of cool, and will look really nice when you get close to them. I'm going to bump up the intensity of these guys a little bit. And then I'm going to change the color of one of them to be more red. Okay. So having shiny materials like this can be used to great effect. It can look really nice. And where it really gets good, so in this case they're just reflecting the light, and then we add an empty object, and we're going to add, we're going to center it in our scene, and we're going to add a component, and it's going to be reflection probe. So the idea here of our reflection probe, and real-time reflection probes probably, yeah, it's tough. So our intensity of a reflection probe, this actually will determine how much additional brightness is going on. So what's happening is now we have reflected light bouncing around, and with that reflected light, it adds light to the scene, but it also means that we will see the reflections of objects in other objects. But as you might expect, right, so there's the objects with the reflection probe there in the middle, and I'm going to zoom in the scene here, right? So they look really different because if you look closely at them, you can see all the other spheres reflected in them, which is really cool, and is also computationally highly non-trivial. And a reflection probe is only in that one certain area, so we're going to bump that up to 100 by 100. We're going to take up the whole scene, and we're going to, There we go. Open up here. So this is another one where be mindful of your reflection probes, right? These are computationally beautiful, and you can start, even as things go by, you can see there's lots of variety in texture as if these were really shiny marbles and they're reflecting the world, and it's really great. Computationally, more than a little complex, and the more of them that you have, the worse it gets. By baking them, by having a baked reflection probe, that is better. Unfortunately, when you do a baked reflection probe, that means only baked objects are going to show up in that reflection probe. So these objects wouldn't show here because they are non-static, but anything that is static in the scene would show. So if we added another floor, right, our floor is static. So we're going to duplicate our floor, and then we're going to make it 10 by 10, and we're going to move it out of the way, or mostly out of the way, right? And so what you should see, it's kind of dark, is that that cube up there will get reflected. Yeah, it's too dark. It's really hard to see. But this cube would get reflected because it's marked as static, and the reflection probes are baked, whereas the other spheres in the scene won't. So real-time reflection probes can create some very beautiful, very immersive experiences, but unsurprisingly, they're going to come with pretty significant performance hits. So that is pretty much it. There are other advanced techniques and tools. Texture atlasing, that's if you're working on reducing the size of your application and maybe some of the memory footprint. So that's where you have, instead of 100 small textures, you have one big texture that's just on a huge canvas, and then you reference different portions of it. Occlusion culling, that's where if one object is in front of another and you can't see behind it, that the occluded object isn't drawn at all. A lot of times right now what happens is you draw from the back forward, and so the further things get drawn first, and then the closer things are drawn later, but then when the closer things are drawn, it completely obscures the further things away, and you waste a lot of time and energy drawing things the further away. There's a lot more about lighting to make informed decisions about, so Unity has some tools about that. The other thing I'm going to say is if you go to project settings and quality, I maxed out at 4 lights, and I did that for a reason. Because here it says rendering pixel light count is 4, right? This is saying that it will support a maximum of 4 lights at any given moment, and it's going to choose the 4 lights that are most important to the camera. So if you can add more lights, you can have a 5th light and a 6th light there, but they're not going to get used until those lights are closer to the camera. And then also a mesh baker, which combines meshes and materials to reduce draw calls. Again, most times when you're working on your first projects and whatnot, you're not going to have to worry about that. So that's where we are. I hope that's really informative, and thank you so much for attending my class. As always, I'm open to feedback. Please let me know what worked, what didn't work. I want to be here for you. You know, these videos are because of some feedback that I had the first time I taught this class. So, you know, anything that I can do to help support your learning, I'm here for. So thank you very much. Appreciate it, and I hope you have a wonderful time building stuff.